Hi, my name is Ben Koenig, and I'll be presenting my project on a titanium dioxide acetone sensor made with a stretch-stabilized stagnation flame in two different precursor phases. Due to their unique geometry and high specific surface areas, metal oxide nanomaterials are valuable for their applications in many fields, including gas sensing. Recent work suggests that many health conditions, including COVID-19, can be monitored through sensing of various compounds in human breath. The sensing is generally done with expensive and slow lab setups, like gas chromatography and mass spectroscopy, that can't be used outside of these labs. Portable, repeatable, scalable, and more efficient metal oxide nanomaterial gas sensors that can be carried in everyday handheld devices and that are fabricated through the flame spray pyrolysis method struggle to replace these traditional processes due to issues in selectivity with interfering gases or repeatability over successive trials. Our project aims to address these issues in sensing acetone, a biomarker for diabetes activity. We also aim to evaluate differences between vapor feed and liquid feed precursors to determine if the more versatile liquid feed method is as usable in our setup as the more reliable vapor feed method. We expand on previous work by leveraging the newer stretch-stabilized stagnation flame process. Our project's implementation fabricates gas sensors that, by virtue of the better particle controllability offered by the stabilized flame, may offer more reliable sensors than the traditional FSP method. In our custom design and built setup, we ignite a premixed fuel in either a liquid or vapor precursor through a dual concentric nozzle, then disperse and deposit the output onto a gold aluminum substrate. These particles can adsorb both oxygen and acetone with opposite effects on their depletion layers. These depletion layer changes can be related to surrounding acetone concentrations by monitoring the sensor electrical resistance, all in a millimeter-sized sensor. After sensor fabrication, we validate our particle morphology here for the liquid phase precursors. Through scanning electron microscopy, we see that we are obtaining particles on the order of 1 micron and of 10 nanometers, the latter being desired due to the size dependency of sensor performance and of crystal structures. This liquid feed particle size discrepancy indicates the benefit of the vapor feed method, which doesn't suffer from the same effect. Through X-ray diffraction of liquid feed particles, we observe a mixed crystal structure with a 3:1 ratio of anatase to rutile. Due to surface oxygen vacancies and adsorption properties, anatase particles are preferred for the gas sensing application. Based on SEM data and existing literature on the crystallized size dependency of these structures, we believe that the larger micron-sized particles account for the bulk of the rutile percentage, indicating a further trade-off of the liquid feed setup. Testing in a chamber through which air or controlled acetone can be flowed through shows a significant resistance drop of roughly 40% upon exposure to acetone, serving as a proof of concept for the effectiveness of the liquid feed method sensor. Our next step will be to test a vapor feed sensor with the expectation that the smaller and more anatase particles will result in better performance. This proof of concept sensor can serve as a starting point for use of our lab's flame setup in producing semiconductor nanomaterials for applications in batteries, photovoltaic cells, and gas sensors. Here, we've shown its potential in fabricating a functional portable acetone sensor that could be tuned with the high controllability of the stagnation flame process to fabricate repeatable and reliable sensors that could be used in portable, at-home diabetes and other health condition monitoring. We've additionally identified various pathways to decrease the particle sizes of the liquid feed setup, which when finalized will open up the possibility of much wider range of fabrication with volatile and thermally unstable precursors. Thank you.